This is part 2 of the video notes for Objective 7, Solving Equations with Inverse Trig. In this portion of the notes, we're actually going to solve some basic linear form equations. Let's start with the simplest equation we can come up with. Cosine x equals 0. Now, we're used to seeing identities and verifying identities. In the case of an identity, the equation is always true for all values of x. This is unequivocally equal to that. This, however, is not an identity. This is considered a conditional equation. For a limited number of x values, cosine x equals 0. Now we're going to solve this two ways. We're going to solve it graphically and we're going to solve it algebraically. So let's go ahead and graph cosine x. And just check our window settings. Let's graph it from negative 2 pi to positive 2 pi. And we know the range of cosine is negative 1 to 1. And since I like to see the whole picture, let's graph it from 2 to 2. Oh, so you can tell by my graph that my mode is not in radians. Otherwise, I would be seeing a sinusoidal curve. So let me fix my mode settings and then regraph our function. There's the cosine curve we expected. When solving a conditional equation, we're looking for the angle values where cosine is equal to 0. So we're basically trying to figure out where the cosine curve intersects the x-axis. Now, when solving an equation, we want to leave our answers in terms of all solutions and not solutions restricted to a specific domain and range like we were doing with our inverse functions. So for this example, I know that cosine x is equal to 0 when x is equal to pi halves, 3 pi halves, negative pi halves, and negative 3 pi halves. So these are all values that repeat on rotation. Here's how we'd like to write our solution. X is the set of numbers where x is equal to, and just like when we wrote our asymptote equations back in the graphing objective, we're going to list the first solution, and we're going to create a formulaic way of finding all of the other solutions. So if pi halves is the first solution and 3 pi halves is the next solution, I know that each solution is pi away from the previous solution. And that's how we solve a basic equation. Let's take a look at one that's slightly more complicated than this example. Let's take a look at the equation sine x minus 1 equals 0. This is not a direct equation. It's going to take some algebraic steps in order to isolate the variable. However, this equation is just like other linear equations or two-step equations that you've seen with a similar structure. We have our variable minus a constant equal to another constant. So we're just going to add 1 to both sides. Where does sine x equal 1? Well, if we'd like to graph it, we can do something a little fancier, and we can say that the first function is sine x, and the second function is 1. Graph both functions. Our solutions are where the two graphs intersect each other. And the nice thing about our graphing calculator, not only can we see these answers visually, it looks like they might be pi halves and negative 3 pi halves, we can calculate them as well by doing calculate, so second trace, and calculate the intersection, which is one of our options. The first curve is sine x. The second curve is 1. We would like to guess our solution. And there it is. The intersection occurs at 1.5707973, comma 1. Well, that strategy works really well when we're trying to approximate our answers, but because 1 is a value on our unit circle, we need an answer that's a little bit more exact. So let's think about all the places on the unit circle where the sine of x is equal to 1. The first value that I think of is pi halves. At pi halves, sine is equal to 1. How long before sine is equal to 1 again? Will it equal to 1 before a full rotation is over? The answer is no. Sine is only equal to positive 1 once every rotation, which means the next answers are 2 pi away from the first. And that's how we solve an equation. Let's try another example. For our last example, we're going to stick to problems written in linear form, but we're just going to keep adding steps to our solution process. So our next example is going to be 3 tan x minus rad 7 is equal to 0. This equation, instead of all real numbers, I'd like you to find your answer for the range 0 to 2 pi. So we're going to stick to one rotation of the unit circle. How are we going to solve this equation for x? Well, we're going to take it very similar to a linear function. Imagine this just said 3x minus rad 7 is equal to 0. We would solve this problem in 2 steps. Add rad 7 to both sides and divide both sides by 3. Except this time it says 3 tan x. So we're going to still add rad 7. 3 tan x is equal to rad 7. We're still going to divide by 3. Tan x is equal to rad 7 over 3. Is rad 7 over 3 a value on our unit circle? Nope, definitely not. Which means in this example, approximate solutions are welcome. So let's use our graphing technology in order to solve this one. Y equals, and on the left side, I'm going to go ahead and put tan x. And on the right side, I'm going to go ahead and put rad 7 divided by 3. Now, in reality, I could have started from the beginning and written this as my first equation and this as my second equation, but I went ahead and showed the algebraic techniques. Here's the graph. You can see it's a standard tangent curve. And there are my solutions. Now, I did restrict my domain from 0 to 2 pi, so I can always change my window settings so that they are also 0 to 2 pi. And then I can see from my calculator screen that I am going to have 1, 2 solutions. So let's use our calculator to find the 2 solutions. And then let's talk about how we can use inverse trig functions to find the same solutions. From the calculator, I'm going to go second calc. From this screen, I'm going to select intersect. It's going to ask me for the first curve, and you can see at the top left corner of the screen, the first curve they're suggesting is tan x, which is true. So I'm going to hit enter. And then the second function is rad 7 over 3. I'm going to hit enter. It asks me if I would like to guess. I'm going to hit enter. The solution that they approximated was the one that my cursor was closest to. So I know one of the 2 solutions is approximately 3.864. The next solution I want to approximate is the first one. So I'm going to do the same thing, but this time I'm going to hover my cursor closer to the solution I'm interested in. Watch the indicator. Keep shuffling, keep shuffling, keep shuffling, and there it is. Now I'm closer to the first intersection. I'm going to hit enter. This is my first curve. Enter. This is my second curve. Please guess my solution. And you can see that my cursor is now over the first solution, which is approximately 0.723. So there you have it. My 2 answers were 3 tan x minus rad 7 is equal to 0. I'm going to move the calculator out of the way, and then off to the left side of my equation, I'm going to find these same solutions using an inverse function. So from here, if I know tan x is equal to rad 7 over 3, then I can say x is equal to inverse tangent of rad 7 over 3. Typing this into my calculator, I get inverse tangent of rad 7 over 3. Reading this solution, I can see that it's 7.227, which is what I have for my calculator, except it's e to the negative 1. This is scientific notation, which means we're going to take our solution, 7.227, and we're going to move our decimal 1 unit to the left, which means x is approximately 0.7227, or as I had in the last example, 0.723. Now, inverse functions have restricted ranges. They only output values within a certain limited range, which means this is only one of my solutions. If you recall, tangent restricts its range from negative pi halves to pi halves. So this is my answer within that range. However, I want all of my answers from 0 to 2 pi. So how can I find the other solution? In order to find the other solution, I like to create a visual. So that this first x is in quadrant 1. I also know that tangent is positive in only one of the other quadrants. Which of the other quadrants is tangent positive in? Hopefully, you were thinking the third quadrant. Tangent is the same in the third quadrant as it is in the first quadrant. So considering x as my reference angle, remember that a reference angle is the angle measured to the nearest x-axis. I can calculate this angle over here. The nearest x-axis is here. If this is 0.723, then x2, the angle measured from 0 to this location, is pi plus 0.723. I'm going to use my calculator to get this value approximately. I'm going to type pi plus 0.723, and I find that the second solution is 3.865, so you can see some rounding issues, which is the same thing I got the first time. That's how you solve a trig equation using both a graphing calculator and algebra. For this last example, we're going to complete an abstract equation where we're going to solve but we can't solve using our graphing calculator because x is a variable and not a number. So we're going to solve x equals negative 4 cosine y over 2 for y. And this is something you're going to see a lot when you're solving equations with inverse trig. We're going to restrict the values of y. So, how do we do that? Just like with the previous equations, we're going to use some inverse operations. For example, I have a coefficient of negative 4. This says negative 4 times cosine y over 2. I'm going to divide both sides of my equation by negative 4. X over negative 4 is equal to cosine of y over 2. From here, there are no more operations outside of the trig functions. So at this point, I'm going to use inverse trig. I know with inverse trig, the input becomes the output. Y over 2 is equal to, we're going to be using inverse cosine. And the output becomes the input. Last step to solve this equation for y. Right now it says y divided by 2, so we're going to multiply both sides of the equation by 2. That leaves me with the new equation y equals 2 cosine negative 1 of x over negative 4, or negative x over 4 essentially. Now that we've solved the equation, let's see why y was restricted from 0 to 2 pi. Well, y is the output of the inverse function. We know that inverse function outputs values from 0 to pi. Multiply those by 2 and you get numbers from 0 to 2 pi. So this restriction on the values of y matched the end result of my equation. This concludes part 2 of the video notes for solving equations with inverse trig. In the next section of video notes, we're going to continue to solve equations. However, we're going to make equations more complex by introducing compositions and by introducing quadratic forms.